Life and death, sickness and health, intervention and watchful waiting. Medical professionals face these choices every day. But with the patient records mounting all around them, today's clinicians must make another choice between the chaos of unstructured data and the sophisticated precision of modern information processing. Such processing has been the entire Aneuryst's agenda.
As technology improves and more information becomes available, most processes need to evolve. Medicine has sometimes been slow to benefit from these changes, and Aneurys set out to show how clinical practice can be transformed by a new workflow approach to diagnosis and treatment that includes freshly developed knowledge discovery and simulation techniques, the automated reuse of clinical data for research, and a comprehensive set of secure information services uniting institutions across Europe.
Aneurys provides a new IT infrastructure for the management, integration, and processing of clinical data. The approach will ultimately be applied to many medical conditions, but we have chosen to work with experts in intracranial aneurysm, an area with significantly fragmented data. Let's see more.
With the Aneurys project, we have developed a comprehensive approach to tackle these healthcare issues. The information we would like to digest is complex to understand, and the integrative approach of this Aneurys project allows us, for example, to better estimate the rupture risk of aneurysm, something that is otherwise very difficult to understand.
Quick look at these medical conditions. Arteries may get a weakness in the vessel wall. At this point, the artery will blow up like a small balloon, and so we are speaking about aneurysms. This is a condition which might occur in patients with very high blood pressure, and it occurs at the main aorta arising from the heart, but they also occur at the base of the brain. So we are calling them intracranial aneurysms.
About 2% of the population will develop an aneurysm, and an aneurysm is at risk of rupture, and if it ruptures, it's a very difficult disease to treat. Indeed, it's in many cases fatal. If we discover an aneurysm, there is need to understand if, when, and how we will treat this aneurysm. So computational information that helps us to do this is of great value to share our responsibility in taking this decision.
So the task for Aneurys has been to assemble a comprehensive array of patient data efficiently, minimizing complexity, and this data comes from a broad spectrum of sources. We know that overall health and lifestyle choices influence disease progression. With aneurysms, for example, kidney disease and smoking are established factors. So our first data source is the patient's health record, which is often not perfectly structured.
Aneurys took a radical look on how data collection can be optimized, and we developed a standardized system for use in hospitals. Medical research usually needs great numbers of cases, and we therefore built a system that connects different hospitals in Europe together. This is a secure system creating a giant database, and other hospitals can easily join the system. We knew that data will be different from the different hospitals, and we also knew that data will be different inside the same hospital. To cope with that situation, we use a method called semantic mediation federation, and we perform the task now automatically.
The Aneurys architecture has been built up using standard web services and newly developed web services to achieve that security. What we do is combine the access to data repositories and remote computing resources linked into the clinical centres. And those remote computing resources provide much higher processing power to the clinics. Provides aneurysm analysts not just with access to data, but also to high-performance computing facilities.
In fact, the Aneurys system is in two parts. There is advanced clinical practice within hospitals, where clinicians have tools for patient data. Using secure grid technologies, we're also able to allow authorized researchers to to work on the entire collection of anonymized patient data that has been amassed across all centers, and may transfer our services there in the future if speed and security standards can be met.
Our second factor is genetic susceptibility.
In Aneurist, we explored the genetics by two different ways. First, we performed a whole genome association study and pooled our data internationally, and were able to identify 6 loci associated with the disease. Therefore, we may be able to identify patients at risk of having an aneurysm using genetics. For the second aspect, we looked at gene expression in blood and were able to analyze and identify markers for rupture. In the near future, we should be able to identify patients at risk of rupturing an aneurysm only by blood.
Treatment choice is usually affected by disease severity. The size and shape of an aneurysm has long been used as a guide to rupture risk. But modern 3D mathematical modelling can bring more sophisticated insights into patterns of flow and stresses in the aneurysm wall.
We've put a lot of effort into the development of software to take a medical image of an aneurysm and to recreate it in the computer. Using this computer model, we can measure lots of physical parameters like shape, structural strain, and fluid shear stress. We believe that there's a relationship between these factors and rupture, and we're currently examining hundreds of cases to see if we are correct.
The starting point for most clinical computer modeling is a set of medical images. Processing this is difficult, so to have any chance of moving to routine clinical use, we needed to make the steps as easy as possible. So we have a new way of identifying and extracting the arteries, which is called segmentation, and that is customized for intracranial scans, and it works well.
To characterize the aneurysm, we transform the segmented arterial tree into three-dimensional computer model, and then we subject this to a realistic computer-simulated blood flow. This process is mostly automated, meaning this can be carried out in a hospital. When we know they are valid, the results will go in the patient record along with the other medical data.
New, less invasive methods of treatment are emerging, and manufacturers, clinicians and patients all benefit from being able to visualize possible treatments.
In the project, we developed 2 approaches for interventional planning. One of them is highly technical and aimed at device designers. The second one is aimed at the clinical application, and it produces results very fast and very accurately.
Let's look at the clinical treatment planning system.
For each patient, the clinician needs to decide whether to intervene or not, influenced by the risk of the treatment. We can simulate this in great detail, allowing to take a decision before the treatment. This one allows to do simulations after the implantation of the device and understand the blood clotting process after the treatment has happened.
Raw information becomes useful when it is shown to have meaning. Aneurist has developed bioinformatics tools to identify and convert relevant information into knowledge.
So medical knowledge is advancing daily. So for example, in the PubMed medical information system, approximately 2,000 publications are published per day. We have built a new system that enables the people to search in this new information daily, and so in this way we are able to convert information which is in public available databases directly to aneurysm treatment knowledge. The starting point for such a thing is the controlled vocabulary that you need for any domain, and for the aneurysm domain we started building the definitive ontology, that's the aneurysm ontology.
Advances in genetic understanding can result in immediate changes to treatment approaches, and are so particularly important.
So the major tool that has been developed is an advanced search engine that allows us to identify recently published works on genetics.
We've seen that medical decision-making is complex. Interpreting the 3D distribution of shear stress on an aneurysm wall is perhaps an extreme example, but it illustrates why information needs to be tamed if it is to be useful. In a final distillation of clinical data, Aneurist includes a risk assessment module that brings together all the source data to provide risk scores for each treatment alternative.
It should then consider all treatment options and provide an assessment of the benefit that the patient gets from each course of action. We have built such a system, and it significantly also calculates the risk of carrying out no treatment at all.
It is the availability of patient-specific support for the no treatment option that offers improved peace of mind for patients and the prospect of reduced healthcare budgets.
So, we've seen that ANURISC has examined and augmented the entire diagnostic and treatment process, and what has emerged is a complete new paradigm for patient care. We are working closely with the European Society for Minimally Invasive Neurological Treatment and hope to bring this work into widespread use in aneurysm care, and also to extend the concept to other medical conditions.
In the ANURISC project, over 250 people came together from all over Europe to unite clinicians and researchers and to develop a better way of managing disease. With the project's work now continuing under the care of ESMINT, we hope we have succeeded.
In 2005, a small group of European experts started a new research initiative called the Virtual Physiological Human. The VPH is the spearhead of European research in the area of information and communication technology for health that makes Europe the leader in biomedical integrative research worldwide. The success of ANURISC is the proof that the vision the VPH initiative advocates is feasible, is real. Bravo ANURISC, molto bene.
So I would say one of the things that is most important is an effort to bridge between different information structures and different information silos. That's a big change.
ANURISC actually has done tremendous work in security and privacy by developing a system based on semantics. The point is that ANURISC is so let's say, so big, so huge project and has so many results